We've all seen them. The face looks realistic, the lighting's perfect, the composition is stunning. And then you look at the hands, six fingers and knuckles going in all directions. It's like something that belongs in a horror film. But it's not a glitch or laziness. There's a very specific and fascinating reason why AI images break the way they do. And it tells you something interesting about how these systems actually work. So let me explain why AI images still don't look right. The architecture that launched the modern AI image revolution is called a Generative Adversarial Network, or GAN. Ian Goodfellow came up with this idea in 2014, apparently sketching out the whole concept in a single night. The story goes that he went home, coded it from scratch, it ran, worked first try. It was generally one of those moments in tech history. Here's the core idea. You train two networks simultaneously and you give them opposite jobs. The first network is the generator. Its job is to create fake images, starting from nothing but random noise and then making them convincing enough to pass as real. The second is the discriminator, and its job is to look at the images, some real, some generated, and correctly pick which one is which. In other words, they push each other. Neither can stay still because every time the discriminator gets better at catching fakes, the generator has to get better as well. And if you run it long enough, you actually get something really useful. But GANs have a serious flaw. They're really unstable to train. Sometimes the generator would figure out that one image consistently fooled the discriminator and just keep making that same image over and over. This is called mode collapse, and it's exactly as frustrating as it sounds. So researchers started looking for something a bit more stable. And what they found now is what's almost behind every image tool that you're actually using. This is diffusion models. And the concept flips the script beautifully. So instead of asking, how do I create something from nothing? The diffusion model asks the question, how do I undo destruction? In training, you take real images and progressively add random noise to them, step by step, until they're completely unrecognizable, pure static. And then you train a neural network to run that process backwards. Given a noisy image, predict what the slightly less noisy version would look like. And you do that thousands and thousands of times, and you've taught the model how to reconstruct images from chaos. At inference time, when you want a new image, you start with pure random noise and just run the reverse process. Walk it back step by step until you get something real. It's not like you're saying make something, it's like you're nudging every step closer towards what you've described. Now, there's quite a few models actually doing this at scale right now. My favorite is Midjourney, which is the creative powerhouse. It used to run in Discord, now has a website, but there was no local installation needed. It produced some of the most aesthetically polished images on the market, and it's one actually designers pay for. Stable Diffusion. This is the open source engine that changed everything because it ran on your own hardware. You could fine tune it and build products on top of it. DALL, which is built into ChatGPT, is OpenAI's entry. Its strength is prompt adherence. In other words, it does exactly what you asked accurately, which sounds really obvious, but it's actually quite hard. Adobe Firefly is the enterprise safe option because every image has been trained on licensed stock, Adobe's own library, which means the legal team will actually approve it. It's integrated into Photoshop, Creative Cloud, etc. for all of the commercial production work. But then, of course, there's Google's Imagen 3, which is one of the most capable models out there. It's now accessible through Gemini. Exceptional photorealism and great detail, but it's underrated because Google really hasn't pushed it as hard as the others. But it's all the same underlying architecture. So back to the original question, why do AI images break the way they do? And hands are the most obvious example, but it's the same logic that explains every failure that you've noticed. First is data distribution. These models train on billions of images across the internet. And in those images, hands are almost never the subject. They're in the corners, they're partly hidden, they're blurry, they're cut off. The model has seen vastly fewer clean, detailed hands than faces or landscapes. Its statistical understanding of hands is just weaker, and that weakness really shows. The second is structural complexity. And a face, for example, follows a fairly consistent template. Two eyes, nose, mouth, roughly predictable proportions. But a hand can be in thousands of configurations, open, closed, mid-gesture, overlapping fingers, knuckle folds. There's an enormous amount of variation and not enough to detail to cover every scenario. Third, and this is really the key important one, is that diffusion models work by consensus. Every denoising step is a prediction averaged across everything the model has ever learnt. And when it's confident, like with a human face or a dog, the consensus is tight and the result looks right. But when it's uncertain, when a hand's mid-gesture or text on a sign or reflections, the model is not really sure. So it averages across conflicting possibilities. And that averaging is exactly why you get the extra fingers, the wrong letters, and the impossible reflections. The model itself isn't malfunctioning. It's doing exactly what it was trained to do. But the cracks appear when the training data is not deep enough. There's a fix being used right now called control length, which is really feeding the model specific structural constraints like skeleton maps and depth maps before it starts generating. So it stops guessing the structure and it fills in the texture. And that's the direction where the whole field is heading, with less hallucination and more constrained generation. So the real reason why AI images look wrong is the same reason in every case, because the models don't see the world, they're learning statistical distributions of the world. And where the data is rich and consistent, the output looks flawless. Where it's sparse or variable, the model averages into something that doesn't quite exist. And that's not a temporary bug waiting for a patch, that's the underlying architecture. And understanding that tells you which tools you can trust and where you need to double check the output, and why throwing more prompts at a broken result rarely fixes it. If this was useful, please subscribe and I'll keep breaking down these complex concepts into bite-sized chunks that people can understand. See you in the next one.